Assalamualaikum and hello everyone. Today my friend and I will be presenting a topic regarding on zeolites. I will start the presentation by introducing myself. My name is Nur Erina Nadira binti Zainal Abidin and my metric number is 191859. I will start the presentation by giving some background introduction about zeolites. The word zeolite is formed from two Greek words which are zeo, that means boil, and litos, which means stone, and these two are referring to boiling stone. Natural zeolites are usually formed as a result of volcanic activities. So when volcanoes erupted, the molten rock within the earth will break through the earth crust and flows out in the form of lava. This will be followed by gases and also thick ashes. As you can see in the slide, structure of zeolites can be divided into two, primary and secondary building units and composite building units. For primary building units, the chemical composition of zeolites are usually composed of elementary structure of nanosilicate framework, which comprises of tetrahedral arrangement that involve two cations, which are silicon cations and aluminium cations. And these two cations are surrounded by 4 oxygen anions. While for secondary building units, it is actually a special arrangement of simple geometric forms that include single rings, double rings, polyhedral, or even more complex ions that link together. I will proceed the presentation by explaining more about primary and secondary building units of zeolites. As you can see on the left side of the slide, there are currently 23 different types of SBUs are known to be existed. So every zeolite unit cell will always have fundamental number of SBUs, and the number of parentheses is actually indicating the frequency of occurrence. Now let's see how PBU join together to form different forms of SBU, the cage structure and the complex zeolite structure. So the cage structure happens when combination of PBUs forms SBU, alignment of which resulted in a cage structure. The next one is chemical model of complex zeolite structure. So as you can see, there are different size of holes, and those different size of holes are representing the channels and cages. Next, after the SBUs are formed, they will be linked together and form a unique structure of zeolite. So as you can see, A, B, C, and D, those are different orientation of secondary building units. So the intersection of lines represent the center of tetrahedral cations. It can be either aluminium or silicon. So on the bottom part, you can see structures of 3 different zeolites and their micropore systems. And you can see the special arrangement of SBUs that contributes to crystalline structure, different type and morphology of different species of zeolites. So secondary building units are usually non-chiral and may contain up to 16 atoms. That's all from me. Thank you.
So hi guys, my name is Anis Manana binti Mamak Khe. My metric number is 194720. So I would like to continue this presentation by explaining about composite building units. Thank you. So in CBUs, they may contain other components such as double rings, concrete cages, and alpha cavities, which we known as the composite building units. From this figure, we can see that there are many examples of composition and size of rings in the zeolitic frameworks, which the most common example of composite building unit is the rings, which size are decided by number of tetrahedrons in a ring and followed by the characterization and naming. Zeolite rings frequently comprise of 4, 5, 6, 8, 10 or 12 tetrahedrons. Based on the figures here, we can see that the cavities formed by the rings have diameter between 2 Armstrong to 8 Armstrong, which it can permit an easy movement of ions between the cavities. For example, we can see for the 10 ring, the diameter is 5.6 Armstrong, and 12 ring, the diameter is 7.3 Armstrong. So the bigger the ring, the more the value of Armstrong. And then we move to the other figures, which the example of composite building units. Each unit is identified with a lowercase 3 character code in italics above on top of the units, and the framework types containing the units are listed below each unit. You can see below each unit there are framework types. And then the rings may be joined to form more complex CPU structures such as prism and cages. Channel and cages from rings form composite building units of zeolites. Next is the development of zeolite. As you can see, for the first type is the primary building units, which is the frameworks of primary building units is either silicon, aluminium, or any other positive charge ion, and combined with oxygen ion. And then move to the secondary building units, which the tetrahedra are connected by silicon or aluminium through their corners of shared oxygen electron atoms to form a wide range of small secondary building units. And then move to the composite building units, tertiary units, which is there are interconnected form of a wide range of polyhedra, which known as the CBUs. And lastly, the structure will form zeolite structure with extended frameworks. And then we move to another figure which shows the structure of 4 selected zeolites and their micropore system and dimensions. As you can see at first diagram is the primary building units, and then move to the composite building units, and then move to the zeolite structure, and lastly their 3-dimension and micropore system. And next is about different types of zeolite naturally occur with dissimilar morphology. As you can see from the figure, there are many examples such as clinoptilolite, modonite, carbozites, and many more. So clinoptilolite and heulandites are isostructural and both generally occur as plates or laths with tabular form. And then modonite usually occurs as fine fibers or as thin laths and needles. Carbazite has a cube-like appearance due to its rhombohedral secondary building units. So, to summarize about the structure of zeolite, we can say that zeolites are naturally porous due to the crystalline structure consisting of 3-dimensional tetrahedral network of silicon and aluminium linked together by common oxygen atoms. And then these pores are a product of interlinked cages resulting from the tetrahedral structures arrangement of atoms, and they are normally of sizes less than 2 nanometer. Hence, zeolite belongs to a group of microporous material. That's all about the structure of zeolite.
My name is Nur Hamiza binti Abdul Hadi and my matric number is 194167. So, today I would like to discuss about the types of zeolite. But before that, I will briefly explain about the classification of zeolite based on the silicon and aluminium ratio. We have 4 of it. So the first one is low silica zeolite. The ratio from 1 to 1.5. For example, we have zeolite A and zeolite X. So both of the zeolite are nearly saturated in aluminium with a molar ratio of silicon aluminium nearly to 1. So as the result, they might contain the maximum number of cation exchange sites balancing in the framework aluminium. So they have the highest cation content and exchange capacities. And the second one is we have intermediate silica zeolite. The ratio is between 2 to 5 ratio, which consists of natural and synthetic zeolite. So, due to the instability of zeolite A and X for an attack by an acid and water vapor steam, it makes the zeolite A and X are less stable than their true analogues. Therefore, we need a zeolite with a higher content of silicon because we want to improve the characteristic for both thermal and 2 acid. And third one is high silica zeolite, and the ratio is from 10 to 4000. We have ZSM5, AU1, monazite, and so on. And lastly, we have of silica, the ratio from 1000 to infinity. For example, our silicates. So there are two types of zeolite, as I mentioned before, which are natural and synthetic. As for the natural zeolite, the process are from the natural ore bodies. There are about 40 naturally occurring zeolite forming in both volcanic and sedimentary rocks, and each of them has a slightly different composition that allow the absorption of water or other molecules. It is non-porous, and they also have the capacity of the cationic exchange, facilitating of the absorption of water, and aluminium, and heavy metals. They also have the exceptional quality of ion exchange, incorporating cations such as cadmium, mercury, nickel, arsenic, or even minerals that are healthy for our human body. So due to this factor, the natural zeolite is commonly used for natural application that is related to agriculture, animal nutrition, water purification, gas filtration, and human health. Next, we have synthetic zeolite, or also called molecular sieve, which are crystalline aluminum silicate that is manufactured in a thermal process. So by controlling the temperature of the process and the composition of the ingredient materials, it allows close control of the structure and surface characteristic of the absorbent. So it has been designed for specific purposes. For example, zeolite E, it is used as laundry detergent. Zeolite X and Y, these are the two types of different fungicide which is used for catalytic cracking. And last one, we have petroleum catalyst, which is ZSM5. It's a branded name for potential zeolite. So it is a porous and processed to get a structure. It prepared by heating together china clay, feldspar, and soda ash, and is processed to get a higher exchange capacity per unit weight than natural zeolite body. That's all from me. Thank you.
My name is Aisha binti Mahir. My metric number is 192789. I'm going to present the properties of zeolites. Okay, the physical properties of zeolite. First is the type of framework structure. So normally based on fully cross-linked tetrahedra containing silicon, aluminium, phosphorus, and occasionally other atoms. And these are generally called T atoms. And the TOT bridges are usually formed by oxygen atoms. The zeolite framework is very open. It means that they have open cavities and contain microscopic channels, sort of like a sponge, and also cages, where cations, water, and absorbed molecules may reside and react, which they are commonly exchangeable. For example, like in solution phase for softening water, by removing calcium and magnesium cations and replacing them by sodium cations. And the channels are large enough to allow the passage of gas species. Second one is the pore size. In absorption process, means that liquids, gases, and suspended matter adhere to the surface of its internal pores. Highly porous solids with very large internal area per unit volume are preferred, as the accumulation per unit surface area is small. So this is very important for high performance as absorbents or catalysts. The third one is the pore volume. Zeolites are microporous, which means that they contain a honeycomb-like structure with pores typically of less than 13 angstroms, 1.3 nanometer in diameter and can therefore readily accommodate simple organic molecules. Pore size of zeolites have a crucial role in determining the absorption behavior of the cations. So some cations may be weakly bound in a large pore as hydrated ions, while in a small pore, the same cation may be strongly absorbed. Let's move on to the chemical properties. First is the acidity. Zeolites have greater acidity at the higher temperature when they are typically employed for real catalytic conversions. The second one is the cation selectivity. Separation distance between the negative charge size determines the cation selectivity of zeolites. When the separation distance are short, the absorption of two or more cations close to each other is unfavorable due to electrostatic repulsions. For example, like zeolites with high silicon to aluminum ratios, such as mordenite, usually have low negative charge density, and this implies that their negative charge sites are far from each other, while in zeolites with low silicon to aluminum ratios, such as lin type A, their negative charge sites are close to each other. Lastly, the hydrophobicity. Tetrahedrally coordinated silica constituting the framework of the zeolite structure is hydrophobic.
Assalamualaikum. My name is Nik Nur Fatin binti Mahazir. My metric number is 192597 and I will explain about the synthesis of zeolites. First of all is natural zeolites. Natural zeolites occurs when volcanic rocks and ash layers react with alkaline groundwater. It also occurs when crystallized in post-depositional environment in shallow marine basins. But natural zeolites are excluded in many applications because of its rarely pure and always contaminated. Next is for synthetic zeolites. There are three methods that used to synthesize synthetic zeolites, which is first is hydrothermal method. Hydrothermal method use water as solvent, base solution as mineralizer, and it reacts at range temperature of 90 degrees Celsius to 180 degrees Celsius. The reactants, which is mainly the reactants to synthesis zeolites, are silica and alumina. So the reactants are usually put inside a Teflon lined autoclave with pressure up to 15 bars for optimum zeolite production. Next is solvothermal method. Solvothermal method use solvents such as alcohols, pyridine, hydrocarbons to produce zeolites. The solvents used varies from non-polar and hydrophobic to polar and hydrophilic. The variety of the solvents will affect the properties of the zeolites. Next is ionothermal method. The solvent used are mainly ionic compound and not molecular called ionic liquid. The ionic nature has an effect on some particular properties such as low vapor pressure. Thus it means different solvent use will affect the properties of zeolites that will be synthesized. From all the three methods, the hydrothermal methods are the easiest and the cheapest way to produce zeolites.
Hi guys, Assalamualaikum warahmatullahi wabarakatuh and good morning. I bid to Dr. Haslina and to all of my friends. So I'm going to proceed with the next part in our presentation, which is I'm going to talk about how zeolite can work as catalyst. The most important part that can make zeolite work as catalyst is the structure of zeolite itself. As you guys can see from the picture here that provided in the slide, the zeolite structure is made up of pores and pore structure. It has like millions of micropores. These micropores are like millions of tube-like, where this tube will trap atoms and molecules that enter the zeolite and let chemical reactions to take place inside it. So that is some basic idea on how zeolite can work as catalyst. So Zeolite is made of three-dimensional crystalline network where the pores itself can absorb molecules and execute larger ones. All these million of micropores also has the ability to exchange cation that makes zeolite can work as catalyst. The next point is zeolite can work as catalyst because due to its high surface areas, and also the nanoporous catalyst contain higher density of active sites. What is active site? The function of active site, I'm going to show video after this so that you guys can get better visual on how active site works inside the catalyst. So the most common industry that use zeolite as the catalyst, I'm going to put one example here, which is the petroleum refining industry. So generally how zeolite work is started with the long hydrocarbon molecule will enter the zeolite through the micropores, and then once the large hydrocarbon molecules inside the zeolite, it will channel with the active sites inside the zeolite, and then after that cracking happen, and then this very long hydrocarbon molecule will crack into shorter variable product, shorter and more variable products such as petrol and alkene. Then I'm going to continue with showing you guys the video on how zeolite work. Okay guys, this is the micropores that I mentioned earlier, and then the hydrocarbon chain enter the zeolite through the micropores, and then once it's inside the micropores, it will channel with the active center. Active center, active site is the same thing, and then cracking happen, and then it will crack into shorter and more valuable molecules. So that's how zeolite works. Thank you so much.